Okay, right, so let's continue. So let's prove now that the complex conjugate of two things multiplied together is it also obeys the field automorphism condition. So for this, is it going to be easier to... Yes, it is. So we're going to now use the exponential representation of complex numbers, the polar form. Let's take two complex numbers, r1 e to the I theta 1, r2 e to the I theta 2. If we multiply these together, which we've done there, it will equal phi of r1 r2 e to the I theta 1 plus theta 2. Then phi is complex conjugation, so we need to complex conjugate this, and to do that you just turn this negative, theta 1 plus theta 2. Okay, so now that's complex. What we now want to do is we want to verify that this is the same as taking the complex conjugate of r1 e to the I theta 1 and then timesing it by phi of r2 e to the I theta 2. So complex conjugate both of those, and what it will become is it will become minus there, minus there. So that's the complex conjugation done. And then all we have to do is multiply these together, and you do that by adding these, multiplying the numbers in front and adding the two exponents, which will give you the same answer there. So complex conjugation obeys field automorphism properties. It also, in this equation here, our 5x squared plus 6x plus 7, it will fix 5, 6 and 7, because what are the complex conjugates of real numbers? They're real numbers, they stay themselves. So that proves for you that if you have any solution of the equation, then its complex conjugate will also be a solution of the equation. So that's why complex conjugation works. It's a field automorphism that fixes the real numbers. It won't work. When it won't work is when you have coefficients of the equation which are complex numbers themselves, because then it will no longer fix these coefficients. It will send them to some other complex number. It will send them to their complex conjugate, and therefore your complex conjugate of your solution to the equation won't necessarily satisfy the same equation. The other time it's a bit useless is in the case where I showed you before of x squared plus 1, where x squared minus 1, where it just maps the solutions onto themselves. But although that's useless, it doesn't break it. It's still working, it's still mapping a solution of the equation onto a solution of the equation. It's just not a particularly useful map. So that's what Galois theory is. That's a brief introduction to it. It's about studying the ways of finding these field automorphisms such that that map roots of an equation onto other roots of an equation, or other roots of that equation, using these group or field automorphisms. And I've given you an example with group algebra. It's a bit more complex to find these field automorphisms in field algebra, but you can find them. And that's it. Thank you for watching.